In the last example, we're going to use a Thevenin equivalent and a step-by-step method to find a VO for t that is greater than 0 in the circuit. In step-by-step method, we look for the constants in the solution to the differential equation directly. This is the conclusion that we're going to use. In this problem, we are looking for VO. VO should have this form: k1 plus k2 times e to the power of negative t over tau. As long as we know k1, k2, and tau, the problem will be solved. So the step-by-step method allows us to find these constants directly. The first step, for t that is equal to 0 minus, this switch is open. We are looking for the current through the inductor or the voltage on the capacitor. The inductor is over here because this is open. The left-hand side and the right-hand side, they are not connected. So we just keep the right-hand side. Before time 0, this is in steady state. This has been in this shape for a long time. This inductor will be a wire in steady state. And the current going through that, let's give it a name, call it IL at a time of 0 minus. And we can find this current. We have two resistors connected in series, and the voltage source is 24 volts, so we can find the current, which is equal to 24, the total voltage divided by the total resistance, right? The total resistance 6 and 6 in parallel, so that will give us 2M. In the second step, at t is equal to 0 plus, and we know that this circuit at t is equal to 0 plus, it will be closed, and we have a different circuit now. And at 0 plus, this inductor will be a current source with the same value of IL 0 minus. So let's draw the circuit. This will be closed. At the same time, there is a current source, and we draw the reference direction going downward. So this is why we will draw a current source over here that goes downward. And this current source will have a value of IL at t is equal to 0 plus, right? And from the continuity property, we know that IL at t is equal to 0 plus is equal to IL at a t that is equal to 0 minus. So we know this current source is 2 milliamp. At this time, we are looking for the initial condition of VO at a t is equal to 0 plus. That is the initial condition, right? We are looking for the initial condition of VO. Since we know the current going through this branch is 2M, we can find a VO at 0 plus by using Ohm's law. By using IL at a time 0 plus times the resistance, which is 6 ohm. That will give us the voltage of 12 volts. Step 3, we're going to look at what happens at a t that is equal to infinity. When at a t is equal to infinity, this inductor will work as a wire. So let's draw the circuit again. And this will be a wire, right? And we are looking for this voltage VO at a time t is equal to infinity. If I use nodal analysis, I select this node as my reference node. Now this node will have a nodal voltage of VO, and its VO at a time is equal to infinity, right? Let's call that a VO. And we can write a nodal equation. The current leaving this node from this branch is VO minus 24 divided by 6 plus VO divided by 6, then plus VO divided by 6 in this branch, then plus the current leaving from this branch, which is a negative 2. That is equal to 0. So we can find a VO that way. Remember, this is the VO at t is equal to infinity. VO at t is equal to infinity is equal to 12 volts. Step 4 is going to find the time constant tau. This problem, we have an inductor. We know the time constant tau is equal to L over RTH, and we need to find RTH. RTH is found from this circuit from here, right? So this is where we're going to look at RTH. And when we look for RTH, we need to set all the power sources to be 0. And to set this current source to be 0, we just need to open that. And for the voltage source, we'll replace that by a wire. So we're going to replace this by a wire so that the voltage will become 0. So RTH is equal to this 6 in series with the other two 6 in parallel, right? So that is a 9 ohm. Tau is equal to L over RTH. L is equal to 4. So that is 4 over 9. They are standard units, so the unit for that is a second. Step 5, we're going to draw the conclusion. Vt is equal to this form, VOT. That is equal to K1 plus K2 times e to the power of negative t over tau. Tau is given already. And we know that K1 is equal to VO at infinity. K1 is equal to that. And K1 plus K2 is equal to the initial condition. K1 plus K2 is equal to the initial condition, which is VO at t is equal to 0 plus. We find it over here, which is 12. And since K1 plus K2 is equal to 12, and we can find K2 is equal to 0. And we will know that VO actually is equal to 12 volts. So this is how we use the step-by-step method to solve this problem. So for Thevenin equivalent method, we look directly at what does the circuit look like for t that is greater than 0. So for t that is greater than 0, this is closed. So the circuit is look like that. So it means that we will be able to find the differential equation from this. So Thevenin equivalent method expect us to find the equivalent to this circuit. So eventually we are looking for something like this. This voltage source will be called a VTH, and the resistor will be called RTH. And we already found RTH from the previous step. So to find RTH is pretty straightforward. We'll copy that over. Let's see how we find a VTH. The VTH is found from here. Don't forget the reference polarity. We're going to use a plus sign on the top and a minus on the bottom. So if we use nodal analysis, we select this node as my reference node, then VTH becomes the voltage on this node. So to write a nodal equation, we have a VTH minus 24 divided by 6, which is the current leaving this node from this branch. The current leaving this node from this branch, that is equal to VTH divided by 6. The current leaving this node from this branch is a minus 2. That is equal to 0. So from here we can find a VTH. So VTH is equal to 18 volts. And we also can find RTH. RTH is found by setting the source to be 0 located from it there, which is the same we have here. So we can find RTH. From the new circuit that we have, we can find the current going through this inductor. Write a KVL equation. The voltage drop on this RTH, that is the current IL. Let's assume the current going through the inductor is current IL, which is defined like this. Voltage drop, the first voltage drop is RTH times IL. The voltage drop on this inductor, that is L times DIL over dt. And the voltage drop on this power supply, that is minus VTH. So we'll put a minus VTH to the right hand side, that becomes VTH. So this is the KVL equation about this Thevenin equivalent circuit. So I'm going to call this step 2. Write differential equation from KVL of a Thevenin equivalent circuit. Now we can put this into a standard form. So this is a standard form. And we already know that tau is equal to R L over RTH, right? This is our tau. By comparing this to the standard conclusion, let me copy this over so that you can better see that. This coefficient in front of dy dt, which is our tau. This is our tau, we find it. And on the right hand side, VTH over RTH, which is the steady state value, which is equal to K1, right? K1, the steady state value, is equal to VTH over RTH. VTH is 18, RTH is 9, so we know that is equal to 2M. We still need to find the initial condition. K1 plus K2 is equal to initial condition. And we cannot find it from this because the initial condition is somehow related to the time before 0. So we need to find the initial condition from here. Look at what happens for the circuit that is before 0. Step 3, we're going to find the initial condition. Or you can say K1 plus K2 is equal to the initial condition. And from the continuity property, IL 0 plus is equal to IL 0 minus. So this is why we are looking for IL at a time is equal to 0 minus. And we find this is the same as what we had before, which is 24 divided by 6 plus 6, which is equal to 2m. So we find K1 plus K2 is equal to 2, and from the previous step we find K1 is equal to 2, so that K2 is equal to 0. Then we can find IL. From there we find IL, let's call this step 4. So we find IL that is equal to K1, which is a 2m. After we find IL, step 5, we'll find the conclusion. Step 5, find VO. Let's see the circuit. So for this circuit, we know the current IL going through this branch is equal to 2M, and we can find VO by using Ohm's law. Is equal to IL as a function of T times 6 ohm. So IL as a function of T is equal to 2M, so that will give us 12 volts. So this is how we use Thevenin equivalent method to solve this problem.